So it's always good to start your design with a blank sheet of paper. Last time we measured the transformer and what it is capable of, and one thing that immediately is obvious that my design goal 0 to 30 volts I can not reach with a single coil. At least not when the I can never reach it. Okay, to be honest. Yeah, part 3. I need both secondary windings. So that makes the first design decision quite simple. I have my transformer and I have, let's say, my small coil and a winding, and I have put them together, and that's it. Simple. And then we put in a nice fat bridge rectifier. Okay. And then we have a nice fat filter capacitor. Okay. And then we have a linear regulator, linear rectifier, whatever. Finished. No, not really. First of all, we should calculate some worst case scenarios, and my first worst case scenario I'm thinking of, and that's the reason, sorry, my little breadboarded L200 based circuit will die under real circumstances, is maximum voltage. So first, maximum voltage. And that's really simple. I mean, we take our upper coil that's without load when mains AC is also at its defined maximum 230 plus 10%. It's 24.6 volts effective. So 24.6 volts effective, and my coil with a lower number of windings as at maximum mains 7.3 volts effective. So 7.3 volts effective, and maximum voltage yeah, no load. Okay, and this gives me a total. Yeah, I will use that arrow several times. So then I have here a total voltage of, and I'm ashamed to say that I'm using the calculator. 17.3 plus 24.6 equals 41.9 volts. So I have here 41.9 volts effective, and that's, let's see what I'm doing, times 2 root equals 59.3 volts peak. Yeah, that's a lot. Okay, then I have my rectifier, and yeah, I'm pretty sure I will not use Schottky diodes here, but normal silicon diodes. Just a second. So at basically no load, or only a few dozen milliamps, I should have a drop around here of, yeah, let's say 1.2 volts. I mean, this is worst case. So 1.2 volts drop around my diodes. Yeah, 2 diodes, each diode 0.6. You could say 0.65 or 0.7, but we're making a worst case here. So 1.2 drop around that little guy. So we end up on the other side with a voltage of was 59.3 minus 1.2 equals 58.1 volts peak. 58.1 volts peak. So, and from this just little calculation, I know that my capacitor will be 63 volt type, of course. And my linear regulator needs also be able to eat 60 volts. And I did that before, I guess. An L200 cannot do that. Yeah, maybe we talk about that one later. So, the second case I want to have a look at is, yeah, how do we second we call it minimum voltage at maximum load. And maximum load is, in this case, 5 amps that I want to draw out here. Yeah, the old girl was capable of, oh, can you read it? It was capable of 5 amps, so yeah, I'm pretty sure the transformer will not die. Okay, minimum voltage. It's a little bit more complicated. So let's see. Do I need a second piece of paper? No. So first of all, we start out with that, yeah, when our mains is at 230 volts and minus 10%, with 20.7 effective plus 14.1 volts effective. Okay. So we have 20.2 plus 14.1. Now it gets complicated, a little bit complicated, because when we are putting a load on, these voltages go down, and the last video we measured, or that at least for resistive loads, that the equivalent resistance of the transformer of one coil was, yeah, about 0.225 and 0.315, and this gives in sum, so I take this value minus 0.54 ohms, yeah, adding these numbers, 0.54 ohms, yeah, times the load I put on it, 5. So this is another 2.7 volts down. And then, yeah, watch the video before. I have, because I have now an inductive load on that and not only a resistive load, I also have to take into account some effects that come from the inductivity of the transformer. And that brings us down on the one coil at 5 amps, and this is just, you know, eyeballed 0.4 volts and 0.6 volts, so the whole thing minus an additional volt brings us to a minimum effective voltage, I'm using green here, of 30.6. So now I have here, yeah, this will be 30.6 volts effective left. Yeah, two worst cases, minimum voltage and maximum load. And just what I did there was I took the yeah, you saw what I did. Okay, and these 30.6 again times square root of 2 is our peak voltage, which is 43.3 volts peak. And I guess in this case, under maximum load, I drop about 2.4 volts. Yeah, look up the usual data sheets. Yeah, at 10 milliamps you have 0.6, 0.7 volts per diode in your bridge rectifier, and if you really go up on cheap bridge rectifiers, cheap old bridge rectifiers, you have 1.1 volts or 1.2 volts drop per diode, and yeah, always two diodes, so 2.4 volts. And this leads to a voltage here of what was it? 43.3 minus 2.4. So we have 40.9 volts peak left here. And we want to supply with these 40.9 volts peak now we're at the end, still 30 volts. And we have a wee bit of a dropout here. And yeah, we drop out. The evil linear regulator is eating some voltage up itself. And I put that at, yeah, L200. That's an interesting question. Let's put that at the moment at 3 volts. Might be a little bit high. Because that's high, we should write down the formulas we're using. So, next thing I want to do, I have now about 49.9 volts minus 3 volts, which I can have a ripple here. I mean, this is not perfect DC here. It's always DC with a kind of a ripple, something like that. What we have here. And up to now we have measured or calculated always the peak voltage, and now I want to know how big is the amplitude here, the ripple. And the V ripple I'm allowed to consume, that is V ripple maximum, or the maximum ripple I can have is my my V peak minimum minimum input voltage I have minus the dropout the part my linear regulator is consuming minus my V out maximum. Simple, isn't it? So my maximum ripple voltage, taking these numbers, is my 40.9 minus 30 at the output minus 3 volt dropout, and this gives us, in our example here, a maximum ripple of 7.9 volts. So this is peak, and we have 7.9 volts. And this is peak to peak, PP ripple. Now, this value, the ripple, the maximum ripple we are allowed to have under these extreme conditions, there I can calculate my filter capacitor from. And there's a nice formula for that. It's basically my V ripple is equal the current I'm drawing. Yeah, the greater the current, the greater the ripple is, times the frequency, yeah, which is after 50 Hertz AC is rectified, it would be 100 Hertz, my frequency, times my capacity. Yeah, simple. The greater the capacity, the smaller the ripple. Yeah, this, and the higher the frequency, the smaller is the ripple, because I'm recharging my capacitor more often. Actually, this is this formula, how like so many others, is a lie, because it follows the following model. If I have my yeah, 0 volts, and I have my rectified sine wave. This assumes the following. The capacitor is charged instantly and then continuously is discharging and then charged instantly, and then continuously at the same rate, at the same current, discharging, charged instantly. And this is of course just an approximation, because another approximation would be the capacitor is, and I need another color now, sorry. The capacitor follows this curve. Yeah, it's charged here. But even that is only an approximation. But the good news is this is good for worst case scenario, because you see this dead area here. This formula still assumes we are discharging here, which we are not. Okay. And so the ripple, or the other way around, our capacitor, if we turn that formula around, which we will do in a second, will a little bit overestimate the capacity we need. So yeah, that's good in this respect. And if we want here the capacity, we simply multiply by the capacity, divide by the V ripple, and we get something like that. So the capacity we need is the greater the current is, of course, divided by the frequency times the ripple. So yeah. And if you take, depending if you live on the 60 Hertz world or on the 50 Hertz world, you get some thumb of rule things where they say, okay, yeah, if you have per ampere, you need that much capacity for that much V ripple. It all goes back to that formula. And if the values they're telling you are not going back to this formula, they're bullshit. Okay, but we can now actually calculate our minimum capacity. And our V ripple is 7.9 volts. So our current is 5 amps, so it's 5 divided by, okay, our frequency is 100 Hertz here, because, yeah, 50 Hertz sinus rectified gives you a 100 Hertz signal. 100 and times 7.9 volts, 7.9 dash 790 equals, oh, and that's a nice number, because these are 6,300 microfarads. Yeah, it's scientific. I'm sorry. Is it 6,300? It's simple. If I take this times 1,000, yeah, 6,000. Let's say 6,300 microfarads. So I know I need a minimum here of 6,300 microfarads. Okay. Still simple. But there's one more case we have to calculate here in our little design consideration here. And the third case in blue, which is not fitting, is maximum voltage at max load. Yeah, again, the 5 amps. Okay, what will we get at the primary? At the primary we will get our 24.6 24.6 plus 17.3. We already done that at some point. So minus our drop over the resistance of the coils, which was 0.54 ohms, 0.54, yeah, times 5 amps. That's the resistive drop, and yeah, the inductive effects, minus 1 volt. So minus 1 equals 38.2 volts. Yeah, there's enough space. 38.2 volts peak, and this times square root of 2 is 54 volts. 54.0. Sorry, this was effective, this is peak. Drop across our diodes is again 2.4 volts, so we have our 54 minus 2.4, so we have here now our peak voltage on this side of 51.6 peak, and we have still these 7.9 volts peak to peak ripple. We already determined our the size of our filter capacitor. And now it gets interesting, because we have, of course, still our 3 volt drop here, but what we can now what we could have calculated before, the 2.4 volts, yeah, which is going in here, and average 5 amps. That means we are burning here 2.4 times 5 amps. Well, that's a little bit much. 2.4 times 5. We're burning here, worst case, 12 watts, which is okay, you know, for silicon rectifier, silicon diode rectifier, 12 volts. Yeah, take the old style and the big metallic cases or whatever, something with a heatsink, 12 watts. It's okay. But how much do we burn here? We burn here, and now we have to go back to the formulas. Our P max for our linear regulator is our V peak minus, yeah, and now comes the V peak ripple over 2 minus our V out. And that's, of course, times our maximum current. And the idea behind that formula, which is also of course an approximation, is if we have 0 volts here, okay, and we have somewhere up here our Ripley voltage, and yeah, I'm using the same model like here, it's softer of course. So this is basically our input voltage into our regulator, and then we have here our output voltage, V out. We have to burn over time at that point, for example, our V peak minus our V out. And at that point of time, we have to burn our V peak minus our V peak ripple minus our V out. Each time multiplied by the current, of course. And what we do with this formula, yeah, minus Vp ripple half, we take the average value. Yeah, so no magic, just more approximations. And that leaves us here with, we said 51, blue collar, 51.6 V peak, sorry, V peak. So 51.6 minus, sorry, not in the shot, ripple 7.9 divided by 2, that's 47.65 minus 30 at the output. And yeah, that's wrong, because we want to have our maximum power we will burn when the output voltage is near 0. Or yeah, just for calculation we can take 0. So for this example, for that case, we say we deliver basically a short, 5 amps on a short on the output at 0 volts. Sorry about that. So I take simply plus 30 gives us 47.65 times 5 amps equals 238 watts. 238 watt. Yeah, okay. I mean, we're burning quite a huge voltage at 5 amps, and here comes a little problem in the design process, or the first snack. Can you see it? These are the heat sinks I have. I cannot mount more heat sinks, and I will not mount a fan. So these are big heat sinks, okay, no question. But the 238 watts might be a little bit too much. So, what could we do? And now it's getting a little bit tricky. We have to introduce something else here. Let me show you. Yeah, if you have seen the teardown of the old lady, that was a part that was included in it. And that's a transformer tap switcher. Yeah. So what we do, we introduce here a switch, somehow controlled that, yeah, can switch between the different transformer tabs, and this is usually done, yeah, you guessed it, by a relay. Okay, let's assume again the same case, 0 volts, but we switch down to this value here. Yeah, let's nullify that. And start the calculation again with only one coil, the big one. Then we have, that's the wrong one, that's the right one. Then we have 24.6 volts effective, 24.6, and sorry, minus only the 0.315 ohms times 5 amps minus 0.6. So we have an effective voltage here of 22.4 volts at maximum load, and this times 2 square root is 31.7 volts peak. 31.7 volts peak leaves us at the other side 2.4 volts minus 2.4 with 29.3 volts peak, 23.9 volts peak, and the same volts peak. We have still 7.9 volts peak ripple. And now we do the same calculation again, and this is, sorry, 29.3. Okay, I know it, 29.3. So we start again. 29.3 minus half of the ripple, so 7.9 divided by 2 equals 25.35, and this times 5 amps, 0 volt output, we have now 127 watts to burn. That's better. That's better. That's 65 watts for each of these heat sinks, and they still got pretty warm, I guess, but yeah, 65 watts they can handle. Unfortunately, we have now to calculate a second worst case, and the second with max load voltage and max load, because 0 volt output, at some point I have to switch the relay and use both coils again, and then we are at that voltages again. But what is that point? I said I have here 29.3 volt peak. That's okay. So 29.3 peak minus our ripple we have 7.9 minus our dropout minus 3 equals 80.4 volts. That is, with just the one coil, I can go up at most to 80.4 volts at the output. If we, I mean, I have my top, I have my my peak value, and then I have my ripple, and then I get my dropout subtracted, and then I get to the maximum output voltage I can give, 18.4. And now we do the other calculation again with the 80.4 volts. And we take the higher numbers again. So 51.6 minus 7.9 divided by 2 equals minus 18.4 equals times 5 equals 146 watts. Okay, this is wrong value. Yeah, so there might be the possibility to tweak these values just a wee bit, to get them a little bit more symmetric when we shift our switch point, when we have to switch the relay a little bit upwards. So we burn more for our 0 volt case, but if we shift that upwards here, we burn less for our yeah, both coils in series case. And we could do that by increasing the capacitance of the capacitor, making that one simply bigger, because when our ripple voltage, which is currently at 7.9 volt, if that gets smaller, we can provide with just one winding of the transformer a higher output voltage. Yeah, that's optimization, and I won't do that by hand. I have to do that in Excel. Just, yeah, wait a second. But before we go into the Excel spreadsheet, I've done the whole thing a little bit more, structured. So we looked at our maximum voltages in red, which gave us the voltage rating of our capacitor, of our filter capacitor. We looked at the minimum voltage at maximum load, the green values, and I added these cases here, the green values, for taking the upper winding or just taking the lower winding, which gave us the minimum capacity of our filter capacitor, and the maximum voltage at maximum load, which we, these were these numbers and these numbers, and we used that, including the ripple voltage, to calculate our power loss when using the upper winding and only the lower winding. And we already know to keep the power loss in a reasonable range, we need a tap switch here. Okay, so now to the Excel. Yeah, sorry for the old school approach here. So we have our input variables, that is our Imax is 5 amps we want to draw out of the whole thing. Let me correct that. We set dropout voltage of 3 volts and on the regulator, and our V out max should be 30 volts. These are the blue values. We had here after the rectifier for using both or only the lower winding of the transformer, and the green values for both windings and the lower windings of the transformer. And that gives us some constraints. We already calculated that by hand. The maximum ripple of 7.9 volts peak to peak. That's simply our lowest upper voltage minus the dropout minus the maximum output voltage we want. Yeah, nothing new. And this is, I already showed you that formula, the minimum capacitance we need in that case. And I think, 6,300. Okay. Now there are no 6,300 microfarad capacitors, so this is just a guideline, and here we can fill in which capacitor size we actually using. That is in this case 8200 I have here in the Excel, and what the actual ripple voltage will be at maximum load. Yeah, let me scroll down. No, well, that's okay. And then we have the, I have already 8200 in here. Sorry, I correct that back to what we said. 6.3. Okay. And then we get, we also already calculated that by hand, the output voltage at which we have to switch from only a single to both windings, which is the lower voltage we get out of the transformer, only from the lower winding maximum, minus the V ripple, again minus the V dropout over the regulator. And this gives us again Imax times the lower voltage minus ripple half minus 0 volts. Yeah. If we operate only on the lower winding, and if we have both windings, Imax minus the upper maximum voltage minus the ripple half minus the switch voltage again, which we calculated here. It's basically the same, but now we can play with the numbers a little bit. So these are, by the way, of course, exactly the same numbers for the power losses we already calculated. So 6,300, I think no capacitors of that size are available. I think it's shift key, 8,000. And yeah, we see a change here. So our absolute upper power loss is a little bit lower, and our lower power loss is a little bit higher. I mean, that's what we talked about. If I decrease the ripple, then I can switch at a higher voltage from the lower windings to both windings. And yeah, so let's play around with it a little bit. The C filter, I think the next size would be 8,200. And this gives us, looks a little bit better. And at 10,000, yeah, that seems, both are below 140. That's nice. It's not a great amount we shaved off here, but yeah, 5 watts plus minus, so we could go maybe with a 6,800. Yeah, just for size reasons and so on. But there's another thing to consider here, and that's the ripple current through your filter capacitor. And yeah, we talk about that in a minute, but 6,800 would be fine. Okay. 8,200 would be fine, and even 10,000 would be fine, or we can go up to 12,000 Now we're really getting a beefy filter capacitor. And yeah, the total power loss is going down, but yeah, there's a price point, and we're basically increasing the capacitor here in 20-30% steps to decrease the power by 1-2%. So yeah, nothing much to do there. However, the dropout voltage, and I think I took the one from worst case LM317 also from the data sheet. If we could do a little bit about the dropout voltage. Yeah, as soon as we increase that, decrease that, say to 1 point, I'm sorry, it's a German Excel, so the comma is the decimal point. Decrease that to 1.5 volt, the dropout, the ripple we can tolerate increases, and so our minimum filter size of our capacitor decreases. And yeah, 1.5 volts is doable, not with an L200 design or LM317 design, but it's doable. And let's see what the, okay, if we start now with 6,800, that looks much better, doesn't it? Now we're below 130 watts and 137. If we go up to the next size, 8,200, yeah, it's completely balanced, and we are now nearer 131, 132 watts. So yeah, we shaved off another 10 watts from our initial figure here, worst case. That's not too bad, but again, price point, yeah, 6,800. I would go just from these numbers with a 6,800 microfarad capacitor. Interestingly, if we now looked at the maximum power loss at the worst case, but if we look at the minimum voltages we have, if our mains AC goes to minimum, yeah, they look equally good. They are not as balanced, but yeah, they are obviously, would be funny if that wouldn't be the case. They are obviously lower. So yeah, everything's good. But there's a second decision point between choosing 6,800 microfarads and 8,200 microfarads. And that is the ripple current. Just give me a second. Yeah, I filtered here at the DigiKey site for fitting 6,800 microfarad capacitors. And yeah, okay, so they have all 6,800 microfarads and are rated for 63 volts, but there is another parameter these capacitors have, and that is the ripple current. And if you look at these numbers, if I go to it, so these ripple currents, they are capable to handle, they are all well below 5 amps. Yeah, well below 4 amps. No, the better ones, they can handle a little bit over 4.5 amp, okay, but below 5 amps. And that is actually a little problem, as I will show you in a second. Blowing this up, I probably, let's take the capacitance here out and select the 8200s. Then you see there are models available with 6 amps of ripple current that can handle, you have to read it, they can handle up to 6 amps of ripple current. Not all of them, but a few, 5.12 amps, yeah, 6 amps, and so on. And if we go to the, sorry, if we go to the 10,000 microfarads, those can handle, yeah, all well above 5 amps of ripple current. Not all of them, but most, 5, 5.7, 6.5, and so on. And now we need to talk about ripple current. So basically, from a power loss perspective, going back to the Excel, decreasing our dropout, our worst case dropout over the regulator from 3 to 1.5 volt had a much bigger effect on the power loss than playing around with the capacitor size here, and not that big. Yeah, we can shave out of here a few watts. Okay, but if we go back here to 3, yeah, well, okay, doesn't make that big a difference. But yeah, so simply from these numbers, 6, 8, 8.2 or 10,000 would be okay. Or yeah, we could go to 12,000. I think we tried that. Yeah, the effect is negligible. Or to say, yeah, we worsen the situation. I think 10,000, yeah, it's okay. But yeah, the ripple current. Let's have a look at the ripple current. So again, we have somehow our rectified sine wave. And that would be approximately 0 volts. And then we said we have the voltage across our capacitor, which looks something like that. And yeah, I'm taking the ideal case. Okay, comes from here. So basically, from here to here, we have a current flow. And make a second 0 amp line, and we can assume that we are discharging the capacitor because nothing is coming from the transformer through the rectifier while we are discharging the capacitor. We have here a current of minus 5 amps going out of the capacitor, and we have only this short amount of time, and I'm assuming this time is shorter than that time, to charge the capacitor. So this is somewhere greater 5 amps. Because in a short amount of time we have to charge it up to the same voltage, or the voltage differential, as we discharged it. From that you can calculate an RMS value, but what the ripple current basically is the RMS current through the capacitor all the time. And yeah, if we look at the equivalent circuit of a capacitor, or at least part of it, you have a capacitor, and the capacitor has a resistance. This is also normally yeah, in the data sheets of the capacitor. It's also a column when you do a parametric search in DigiKey. So yeah, the thing is, if current is going in and going out, we have a loss here, and that means we are creating heat inside our filter capacitor. And as I said before, the smaller capacitors, 6800s, they are almost all rated with a ripple current below 5 amps. So if you mistreat them and induce a ripple current higher as 5 amps, they get hot. I mean, if you go, say, it's rated for 5 and you go to 50, they probably explode. I don't know. But if it's rated for 5 and you go for 10 amps or so RMS ripple current, they heat up and they age much faster than intended. So if they say normally it has a lifetime of 2000 hours and you increase the ripple current, that lifetime might go down to only 1000 hours. And as I said, if you increase your ripple current enough, they might blow up. The thing is, the smaller your ripple voltage is, the more extreme becomes the difference between the time you are loading and the time you are unloading or charging your capacitor. So basically, if I do this a little bit more extreme, if we would have only, yeah, let's do it on this side, only a very small ripple voltage, or smaller ripple voltage, yeah, coming over from here, then our timing is different. One color. Then we suddenly have a very, or a longer stretch, minus 5 amps, and we have only a shorter stretch where we recharge it, and this should be much bigger. And yeah, this is simplified. It's not really a rectangular waveform. You know, it will look something like that. But yeah, for the moment, that's enough. But here's one rule: if your maximum current you're drawing out is 5 amps, then your RMS ripple current will never ever be below 5 amps. It will be best case at 5 amps, but possibly lower, higher than 5 amps. And so the 6,800 microfarads, as we saw, can only, in most cases, only the most expensive one could handle a little bit over 5 amps. But yeah, simply going by the ripple current, we cannot use these. We have to use one side bigger. At least 8,200. They were available in ripple currents a little bit bigger than 5 amps. So that brings us back to our design decision, or how to design the thing. So yeah, we already know this linear regulator must be capable of 60 volts, and we have a new minimum value here of 8,200 microfarads because of the ripple current. And I won't calculate the RMS ripple current, that might be a little bit too complicated, but yeah, 6,300 is, even in the best conditions, too small to handle. 6,800 microfarads is, even in the best conditions, not enough to handle the ripple current, and 8,200 might be able to handle it. Yeah. What else? The electronic controlling our transformer switch. Yeah, I have to go back to the notebook just a second. So we said we take a little bit of better linear regulator with just a dropout voltage of 1.5 volts and a capacitor of at least 8,200 microfarads, and this gives us here at the optimal switching voltage these power losses of 130 something watt, which is okay with the big heat sinks. But if we look at the lower voltage case here, so our AC in is at the absolute minimum, we see that our switch voltage, which we have to switch to the upper, is of course switch to using both windings of the transformer, is of course lower. Yeah, because transformer output voltage is lower, and it's basically the same formulas, but for the green, for the lower voltages. And if we would use a fixed switch voltage, we would have a problem, because if I take these 15.5 and put them in here, 15.5, mixing American and German, then suddenly our our power loss is again in a region which is not acceptable. So our switch voltage depends on our lower transformer voltage, of the voltage coming out of the lower winding of the transformer, minus ripple, which is the same, minus dropout, which is the same, plus, you have to measure the output of your linear power supply. So our switch basically has two inputs, or the electronic of our tap switcher will need to have two inputs. So of course we have to measure the output voltage, and this will be a crooked line from here to our output. So this is the sense line. But we need a second sense line from our lower winding. And with these two voltages, our output voltage and our voltage on the lower winding, we can decide when to switch the tap. So here you have it. That's what the power supply should look like, and I very much would like to get that down to 1.5 volts, or maybe even lower. I mean, in the end it will not be an LM317 or L200 design or something like that. I have to think about 60 volt capable linear regulator handling 5 amps. Might be hard to find there a real easy solution. Okay, but maybe you have other requirements, but to wrap it up, if you do a power supply design, you have to check for these three things. First, the maximum voltage, depending on your, forgot the core, your maximum input voltage, so you know what your parts need to handle in terms of voltage. Your minimum input voltage, so you can calculate what your maximum ripple is that you can tolerate without any dropout on your output, and your maximum load, and your maximum voltage you get out of your transformer at maximum volts to calculate your maximum power losses in your linear regulator. And if you check these three cases, you should be fine and be able to set up your linear power supply accordingly. Okay, now this kind of has become, by accident, kind of a tutorial. Not really. Kept the math at bay, I hope. I don't know where to proceed from here. I have to think about that and how to design this little thingy. But for now, thank you for your time and bye.